Okay, so hello, my name's Neil Walton. I'm about to teach a first year probability course at the University of Manchester. So for those students and anyone else who's interested, I was essentially going to go through the main material that course is going to cover, the examples, the definitions, and essentially give a sort of reasonably comprehensive cover of probability at a first year university level. Okay, so what I'm going to do today is essentially just discuss sort of what probability is, at a very basic level, and some of the basic definitions. Okay, and then we'll continue on into more depth into the sorts of calculations one might want to do with probability, both in terms of counting and in terms of the kinds of operations that we might want to do in order to do different sorts of probabilistic calculations. Okay. All right. I'll start and then. Okay, so what we're going to do is sort of an introduction to probability, and I might add that I'll try to prepare some notes, or I started to prepare some, but in the interest of time, because that's fairly time consuming, I'm just going to do everything handwritten here. Also, as a result, that slows the pace a bit, which is sometimes useful if you want to think about things. On the other hand, if you're finding this a bit slow, then, well, since it's uploaded to YouTube, and you can always click on the bottom right hand corner of your window and speed up the speed of the video as well, if you wish. Okay, so let's talk a little bit about probability. So what is probability? This is sort of a very high level discussion, not really a mathematical discussion as such, a little bit more philosophical than that. But I want to get some of the key ideas down from the beginning. So what is probability? And this is sort of a little bit of a personal viewpoint, though I imagine other people agree. So let's suppose I throw a coin 100 times. Okay, and I got 52 heads. Okay, so the coin either lands heads or tails. Okay, and a question for you to think about is, well, how many heads should I expect? Okay, and the answer to that is that if you think about it, it should be about 50. Okay. Also, do feel free to write down what I'm writing here. You don't have to, you can also just listen. For the students in my course, I'm going to recommend that they write down everything that I write down, because it sort of forces you to think about what I'm doing as you go along. Okay, so 50 heads. Should be expected. Okay. Okay. It isn't necessarily what happens. There's a little bit of an error of 2 here, and in fact later on in the course we'll focus quite a bit on what these errors should look like. Okay. Now, another question. So let's do another experiment. Okay. Let's consider another experiment. Okay, I throw a dice. Okay. And the question is, if I keep throwing the dice, and I do that forever, So if I keep throwing the dice forever, okay, then what proportion of the throws are a 5? Okay, so I throw the dice, it's numbered 1, 2, 3, 4, 5, 6. Okay, and let's assume it's not a biased dice, it's just a normal, regular, unbiased dice. Okay, I throw it, and I just keep throwing it forever. Okay, and I'm going to ask what proportion of the time do I get a 5? Okay. Now, if you think about it for a little bit, you should see that the proportion that you get is 1/6. Okay. Sometimes people in class think 1/5, and remember that the actual number on the face of the dice has nothing to do with the probabilities. As I could put, yellow bananas or green apples and colour the dice differently. Okay. It still wouldn't change the fact that a dice has 6 sides. Okay. And all things being equal, then the chance of a 5, okay, should be 1/6. Okay, so yes, you should find that the probability of this outcome is 1/6. Okay. Now, some comments on that. So this is sort of really what a probability is. It's you sort of imagine in your mind that you have an experiment and you're going to keep doing that experiment forever. Of course, that's not realistic to be able to do an experiment forever, but you could imagine what would happen if I just kept doing something over and over and over again. Okay. And a certain proportion of the time, we can expect something to happen. Okay, so in the case of the dice, we can expect a certain proportion of the time to get a 5. Okay, and with that, we get a number that's between 0 and 1. Okay, so 1 meaning that event happens all the time, or 0 that it never happens, or in this case, 1/6. Okay. Okay, so notice that the probability in some sense is kind of an idealized limit, okay? If I kept doing something forever, then it's the idealized sort of proportion of time that something happens, okay? In fact, this idea that if I kept doing something random forever, and then it would converge towards some deterministic number like a 6, actually has a naming probability, so it's called the law of large numbers, okay? And so from our mathematical assumptions, that's something indeed we want to actually be able to prove as well. Okay. On the other hand, we also sort of take it as our definition from the beginning that there should be this long run proportion given by 1/6, which represents our probabilities. It gives a weight for the different outcomes that can occur. In the case of a dice, the weights are all equal and there are 6 outcomes, so we get a probability of 1/6. Okay. Notice that 1/6 number is arrived at by essentially just counting up the number of faces on the dice. The same with the coin, it's got 2 sides, so we end up with a half, okay? And thus we expect a half of those 100 coin throws to be heads, okay? So that gives an idea that somehow probabilities are to do with long run averages, like the 6, okay? That we have sort of expected behaviours, like the 50 heads that we got, but there can be some errors, like that error of 2 between the 52 heads that we got above here, okay, and 50, okay. Okay, so next, a slightly tougher question, or slightly more interesting question. not necessarily more difficult. Okay. So I'm going to start, or stop and start, a stopwatch. I can actually do that in front of you because I've got my phone. I do own a dice and I do own a coin, obviously. Some, not many. But seeing as it won't fit on the screen very well, I can show you it this way. Okay, so I have a stopwatch. Okay, and what I'm going to do is I'm just going to stop it every now and again and look at the final digit. Okay, so in this case I've got a 5. In this case the last digit is a 1. Okay, and I just keep doing this. I just let the clock go and stop it, and in this case I'm getting a 7. Okay, and we just keep doing that. Alright, and then I ask the question. So I stop and I start a stopwatch and look at the last digit. Or digit, sorry. Sorry, my spelling's not the best. Okay. So I ask the question, what is the probability, meaning what is the long run proportion of time that I expect to see, in this case, an even number. So what is the probability that this digit is an even number? Okay, so think about that for a second. Okay. All right, and so you should probably think that the answer is a half. Okay, so yes, if you thought that correctly, it's 1/2. Again, like with the coin. Okay. So how did we go about doing that calculation? Well, it's slightly different to the coin, because the coin only had 2 things that could happen, and then only we looked at the chance of a heads, and since things were equally likely to happen, it was only one of the 2 outcomes. Okay. In the case of the stopwatch here, when we ask for the probability of an even number, well, there are 10 things that can happen for that final digit. It can be 0, 1, 2, 3, all the way up to 9. Okay, and half of those, okay, are an even number. And given that all of those are equally likely to happen, then we expect the probability to be half. Okay, so again, we've sort of counted up and looked at a subset of the sets of outcomes that can occur, and the event that we get an even number, okay, is sort of the sum of those. It's 5 out of 10. Okay, so really, we think of the chance of the digit being a 0 as being 1/10, then the chance of a 2 being 1/10, a 3, a 4, a 4, a 6, and an 8. Okay, so the digit being a 0, the digit being a 2, the digit being a 4, the digit being a 6, and the digit being an 8. Well, there's 5 events there out of 10, so I'm going to get a half out. All right. Okay. So that's one point in terms of the way that we sum up or deal with probabilities when there's more than one outcome, or we're considering sets of outcomes. Okay. Another point that's a little bit more philosophical is that we can think about the actual stopwatch itself. Okay. So the stopwatch itself, in principle, is deterministic. Okay, but we find that we're actually introducing randomness into the system by me pressing stop on the stopwatch. Okay, now that's something that occurs quite often, that the error that I introduced by interacting with the deterministic system introduces randomness into that system. Okay? So this is something similar to this is more of a kind of physics view of randomness. So if we looked at the gas particles in the room that I'm in right now, okay, they're all following deterministic laws, okay. You could say Newton's laws, okay, for the way that different particles interact, collide and bounce off each other, okay. These are reversible interactions, okay. So why should it be that we've got a kind of uniform distribution of the particles around this room? Indeed, if I put all of the gas within this house into one single corner of this room and then let the clock tick, okay, in principle that's a deterministic system, but yet when I observe it here now in the house, it's uniformly distributed around the house, the gas, okay. And that's essentially because a similar idea that we've introduced small perturbations into that system, or there are small perturbations in that system that we don't necessarily observe, and those, as we let that deterministic system evolve into something that's much more random, uniform throughout this specific house. Okay, so in some sense, randomness is in many different systems, even ones that you might consider to be quite deterministic as well. Okay. I mean, one key thing to say before I sort of get on to slightly more concrete things is that in each case, okay, there is randomness in the examples that we've discussed so far. Okay. So there's randomness introduced. Okay. But I don't mean random like random, completely random, like that's such a random comment you couldn't possibly guess what was going on. Okay. In each of these cases there's randomness, but it's a quantifiable randomness. I can associate numbers, okay, in order to quantify how likely or the relative likelihood of different events. Okay. So, however, the randomness okay, is quantifiable. Okay, so it's not completely unknown. Okay, we can get some measure of it. Okay, so essentially probability is the area of science and mathematics that studies this quantifiable randomness. So the y here. Okay. So sometimes, so that's what probability is. So sometimes people kind of conflate probability and statistics and say that they're the same thing. So probability is more the mathematical area that discusses and tries to understand the quantifying of this randomness. Statistics is essentially the extension of the ideas of probabilities, where you incorporate data that you would observe in the real world, and how does that help inform your quantifying. Okay. Then, in addition to that, sometimes people kind of conflate machine learning and statistics together. Machine learning is sort of the area of statistics, shall we say, or statistics is the area of machine learning, depending on your viewpoint, or data science, or whatever, that essentially takes account for the computational considerations that go on in doing statistics. And many statistical procedures involve a lot of optimization. There are computational issues surrounding that, and also when you're accessing large amounts of data, there are computational considerations as well in order to do any sort of inference procedure through statistical methods. Okay, so machine learning essentially looks into the computational and optimization aspects, let's say, of statistics. Okay, and then what's, say, then beyond that, another thing that also gets conflated into these things is things like artificial intelligence. And artificial intelligence is sort of the augmentation, let's say, of machine learning with making decisions. Okay, so you essentially go from sort of something that quantifies randomness to something that tries to infer and estimate randomness to something that you can implement and then do statistical procedures with, and then to a process where you make decisions. Okay, that's probably a reasonable approximation. There's plenty of debate about what the differences are between these different subjects, but I think that's a reasonable approximation of what each one is. Okay. One of the things I do say to a lot of undergraduates when they're starting is it's very important during our undergraduate to try and understand, particularly for employability reasons, how to work in a computational way with different probabilistic and statistical methods. Okay, nowadays there's a lot of prevalent data. Okay, and be able to do things with that and to make the most of your kind of probabilistic and statistical education, then it's important to be able to implement different algorithms computationally. Okay, so I'll try to discuss that a little bit. But okay, that acts as a good introduction, and next we'll get on to more of a mathematical take on probability